Last week, I asked you to help me measure the radius of the Earth, and wow, did you all rise to the challenge. Over 70 people from all around the world joined in. They sent me data from as far east as Japan, as far west as Vancouver Island, as far north as Iceland, and as far south as Argentina. Each red dot on this globe is where someone took a measurement and sent in the data. It's amazing how much we can learn about our planet from something as simple as a shadow. One of the cool things about getting time lapses from around the world is the ability to compare how the shadows move in different hemispheres. Any shadow in the northern hemisphere will move clockwise as the day passes, while any shadow in the south will turn counterclockwise. It's almost as though modern clocks were based on sundials built in the northern hemisphere, but that's crazy. Let's take all this data that people sent in and figure out the radius of the Earth. There are a few different ways of analyzing these measurements and using them to derive the radius. However, I'm going to stick with the same approach Eratosthenes used. By going through the measurements, I can find all the pairs where the location of one lies almost due north of the other. Pairing the data in this way lets us calculate the radius as simply as possible. The downside is that many of the data points won't be used in the final calculation. That's why it's great so many people participated. It meant more usable data points. With these pairs, getting the radius of the Earth is just trigonometry. The first thing we need is the angle of the shadows cast at the two locations. To get this, we take the measurements of the length of the rod and the length of its shadow, and then make a right triangle with them. The angle can either be measured with a protractor or calculated using the arctan function. The function is preferable when dealing with a lot of data because a spreadsheet can do all the calculations instantly. So the angle theta is equal to the arctan of the shadow length over the rod length. The sun is so far away from the Earth that the light comes in at nearly the same angle no matter where you are on the planet. We'll use this to figure out how many degrees separate any pair of points. Again, using trigonometry, we see that the angles separating the pairs of points on the Earth is related to the shadow angles by phi is equal to theta 2 minus theta 1. As a rule of thumb, the greater the angle separating the points, the better our measurement of the Earth's radius will be. For this experiment, the pair located at Rio Negro, Argentina, and Massachusetts, United States, had the largest angles separating them. Under the approximation that the Earth is a perfect sphere, we can relate the angle separating the pair to the total number of degrees in a circle, 360, to the ratio of the ground distance separating the pair and the total circumference of the Earth. That means we get a measurement of the circumference of the Earth for every pair, and dividing that by 2 pi gives us the radius of the Earth. The only other input we need is the actual distance between the points. In Eratosthenes' day, he had to estimate that distance by using the time it took to travel between the two cities on camel. The higher quality maps of today means that we don't have to fund a camel expedition between Argentina and the US. Doing that calculation for every pair of data points gives us the following radii for the Earth. Averaging the 5 results gives us a radius of 6,686 kilometers. That's only 5% off the actual value of 6,371 kilometers. Or, in units Eratosthenes would understand, 6.6 camel days, assuming a camel running speed of 40 kilometers per hour. Ha! Take that, Eratosthenes, with your 16% accuracy. Why don't you ride your camel back to your library? Oh, right. All kidding aside, it's easy to take for granted just how clever Eratosthenes had to be to come up with this measurement. All because he read about someone seeing their shadow at the bottom of a well. Thanks for watching. To everyone out there who participated in the experiment, you guys are awesome. Have a well-deserved internet fist bump. Come on, don't leave me hanging. This project would not have been nearly as successful if Thunderfoot hadn't posted the video on his channel. So give him a big thumbs up. I couldn't have attracted 70 people to do this experiment on my own. Lastly, I really want to thank the parents who got their kids involved in this experiment. After all, if you don't talk to your kids about science, who will? So be sure to subscribe if you don't want to miss out on future content like other experiments or just listening to me waffle on about various physicsy topics. And remember, when in doubt, use science.